Section 8.2, Compositions and Inverse Transformations. If T from V to W is a linear transformation from a vector space V to a vector space W, then T is said to be one-to-one if T maps distinct vectors in V into distinct vectors in W. If T from V to W is a linear transformation from a vector space V to vector space W, then T is said to be onto, or onto W, if every vector in W is the image of at least one vector in V. For our first theorem, if T from V to W is a linear transformation, then the following statements are equivalent. T is one-to-one if and only if the kernel of T is equal to 0. Let's prove this. Since T is linear, we know that T of 0 is equal to 0. That's a property of linear transformations. It maps 0 to 0. Since T is one-to-one, there can't be any other vectors in V that map into 0, so the kernel must be 0. That's all the vectors that map into 0. Alright, let's prove that B implies A. So let's assume that the kernel of T is equal to 0. If U and V are distinct vectors in V, then U minus V must not be equal to 0, right? Because U is not equal to V. So that means that the transformation T applied to U minus V must also not be equal to 0, because otherwise the kernel would have a non-zero vector in it. So then, since T is linear, we must have that T of U minus T of V is equal to T of U minus V. That must be not 0. So that means that TU is not equal to TV whenever U is not equal to V. In other words, T maps distinct vectors in V into distinct vectors in W. In other words, it's one-to-one. Let's do an example. How about we let T from R2 to R2 be the linear operator that rotates each vector in the plane about the origin through an angle theta. Let's determine if it's one-to-one and onto. So first, how about we draw what's going on here? We have an xy axis, and we have, let's say, some vector u. So that rotates to another vector tu. So here's u, here's tu, and that goes through an angle theta. And we could have another vector v. Let's see, something like that. So that could be v. Remember, this other vector was t applied to u. So then we could also rotate v. And if it's by the same angle theta, then we'll get a different vector tv. So I think it's pretty clear from our picture that T does in fact map distinct vectors into distinct vectors. If U and V are different, TU and TV will be different. So that means that T is one-to-one. Actually, a better way of saying it is if TU and TV are different, they must have come from different U and different V's. Notice also that every vector here that we can get by rotating some other vector around. So every vector in R2 is the image of another vector in R2. So that means that T is onto. Let's let T from R2 to R2 be the linear operator that maps points orthogonally onto the x-axis in R2. And let's see if this transformation is one-to-one and onto. Okay, so we'll draw this now. So here's x and y, and let's see, we need a point, and it's going to map orthogonally onto the x-axis. So let's say we have a point over here, P. Then P will map straight down onto the x-axis at some other point, let's say M. If we have another point, let's say Q over here, then if it lines up with P, it will also map onto N. Every single point along this line is going to map straight down onto the x-axis onto the same point, M. So that means that distinct points map to the same point. So that means it's not one-to-one. Okay, what about being onto? Well, what if I looked at the points P and Q? There's no way I could get those out of this operator T, because T projects everything onto the x-axis. So any point floating around that's not on the x-axis can't be a result of the transformation, because the transformation would have sent it to the x-axis. So there's no way to get points that aren't on the x-axis out of the transformation. So it doesn't hit every point in R2. So points off the x-axis are not images of any point in this transformation. So that means that this transformation is not onto. For our next example, let's verify that this linear transformation T1 and T2, defined by these T1 and T2 given, are both one-to-one and onto. Well, how about we look at the kernel of T1? Maybe I'll write it like this. So the kernel of T1, well, that's the same as the kernel of T2, because both of them are 0. By our previous theorem, the kernel is 0 if and only if our transformations are one-to-one. So that means that both T1 and T2 are one-to-one. It should be pretty obvious here that the kernel is 0, because you would have to have A, B, and C, D in here being 0 in order to get them 0 over here. So that means that you must have this thing being the 0 polynomial, so they must send 0 to 0. There's another way to get zeros out of it. And same thing over here, all your entries would have to be 0, so it must be the 0 matrix. So let's check now if they're onto. Well, I mean, it should be pretty clear that you could take A, B, C, and D any way you want. They could be chosen to produce every vector in R4. So that means that T1 and T2 are onto. Next up, let's let Pn to Pn plus 1 be the linear transformation that sends P to x times P of x. We discussed this in example 5 of section 8.1. Is T one-to-one? Is it onto? Well, let's look at two different polynomials. Let's say P is the vector equal to the polynomial P of x given by C0 plus C1x and so on through Cn(xn), and we'll let Q be a distinct polynomial, Q of x equal to D0 plus D1x through Dn(xn). Okay, so these guys are distinct, and that means that if I look at T of P, well, that must be C0 times x plus C1 times x squared, and so on, through Cn times x to the n plus 1, because we're just multiplying everything by x. And similarly for TQ, that'll be D0x plus D1 x squared, and so on through Dn x to the n plus 1. And if these guys were distinct to begin with. The coefficients are distinct. These guys must be distinct as well because they have different coefficients. Okay, so that means that t is 1 to 1. However, it's not onto. Because you would have to multiply anything by x. So you always end up with at least x to the first power. You'll never be able to get constants. For example, if you took t of p, for any p, you would never be able to get 1. Because if you put in, let's say 1, you multiply by x, you would have x out of it. There's nothing you could possibly put in there to just get 1 by itself. 1 is a polynomial. It is in Pn plus 1, so this thing is not onto, it doesn't hit every polynomial. Next, let's let V be R infinity, the sequence space discussed in example 3 of section 4.1, and let's consider the shifting operators on V given by T1 and T2. Let's show that T1 is 1 to 1 but not onto. So notice T1 takes u1 through un all the way up to just keep going forever, and it moves everything down and puts a 0 in the first entry. So everything gets moved down, u1 gets pushed down, whereas T2 just drops u1 and starts at u2 instead. So it just drops the first entry and then just keeps going infinitely. So for T1, notice if I have any different u1, un all the way up to infinity, putting a 0 in, well, that'll still produce something different. Or this, looking backwards, if I have 0 all the way up, u1 keeping going, then that would have to come from a distinct u1, u2, and so on sequence. So the 0 doesn't make them not distinct anymore. Distinct sequences in R infinity have distinct images. So T is definitely 1 to 1. However, it's impossible to get vectors that don't have a 0 in the first entry. So for example, no vector maps into 1, 0, 0, and so on. The sequence just has a 1 and then zeros afterwards. So it's not onto. Notice to see that transformation is not onto, you just defined a single example that breaks it, a single vector that doesn't have an input. Let's show that T2 is onto, but not 1 to 1. Well, notice you could take U2, U3, and so on to produce any vector you wanted. So you could choose them however you like. It doesn't matter that you're missing U1, you just start with U2 and you choose all the rest of them however you want. So these guys can be chosen to produce every sequence in R infinity. So that means that T2 is onto. But to see that they're not 1 to 1, well, you could have two different vectors, or two vectors that have different u1s that makes them different vectors, and they could both map into the same one because you're losing u1. So for example, if I looked at the vector 1, 0, 0, and the vector 2, 0, 0, well, those both would map into the vector 0, 0, 0, because it just drops the 1 and the 2 either way. So they both produce the same vector, it must not be 1 to 1. For example 6, let's let D from C1 to F be the differentiation transformation discussed in example 11 of section 8.1. Is D 1 to 1? Well, how about we look at the differentiator operator applied to x squared? Well, that would be 2x, right? But if I took the derivative of x squared plus 1, that would also be 2x. The derivative of any function up to a constant would be the same, because the constant will always have a derivative of 0. So that immediately tells you that D is not 1 to 1. If V and W are finite dimensional vector spaces with the same dimension, and if T from V to W is a linear transformation, then the following statements are equivalent. T is 1 to 1, if and only if the kernel is 0, if and only if T is onto. So this is for finite dimensional vector spaces with the same dimension. So as an example, let's look at TA from Rn to Rm. That's multiplication by an n by n matrix, A. Then when is TA 1 to 1 and when is it onto? Well, automatically, we know that TA is not 1 to 1 if the dimensions don't match, or in other words, if the dimensions don't match in the case where m is less than n, right? Because if m is smaller than n, then we're losing some information from over here. It must be we're sending different matrices here to different matrices over here, and it is not onto in the opposite case if n is smaller than m, right? Then there's no way you're going to be able to hit every matrix in Rm. If m is equal to n, then it depends on your matrix A, or more specifically, it depends on the rank of A. It turns out that if A is invertible, then TA actually is 1 to 1 and onto. This isn't too surprising, since if A is invertible, then you have a transformation that can go backwards from Rm to Rn, given by A inverse multiplied by some matrix X. So you kind of have an inverse transformation over here, so it makes sense that the matrix being invertible would be enough over here to be able to say that the transformation is 1 to 1 and onto. If TA is a matrix transformation, then TA is 1 to 1 if and only if the columns of A are linearly independent. TA is onto if and only if the columns of A span Rm. Let's prove A. So it follows from theorem 8.2.1 that TA is 1 to 1 if and only if A has nullity 0, which is the same thing as saying that A has rank m, which is the same thing as saying that the m column vectors of A are linearly independent. To prove B, to say that TA is onto is the same thing as saying that the system Ax equals B has a solution for every vector B in Rm. But this is true if and only if the columns of A span Rm. So not so difficult to prove that. That adds to our equivalent statements. Now we have a couple more here. We have the kernel, the range, TA. Whole bunch of equivalent statements now. As another example, let's let T from R3 to R3 be the linear operator defined by this formula right over here. Let's determine whether T is 1 to 1, and if so, let's find T inverse. So how about we write out the matrix A over here. So we'll give that by the coefficients that we have. So for the first entry over here, we have 3 for x1, 1 for x2, and there's no x3s over here, so 0 for x3. So I'll put 3, 1, 0. For the second row, let's look at the second entry in the output, so that's -2, 4, 3. And lastly, we have 5, 4, -2. So that's our matrix A for the transformation. Let's look at A transpose. Well, that would be 3, 1, 0, -2. Forgot the minus over there. -4, 3, and 5, 4, -2. If I want the adjoint of A, then that would be -4, 2, 3, 11, -6, -9, -12, -7, -10. And I can compute the inverse using the adjoint to get that A inverse is 1 over -12 plus 11 times the adjoint, and that's 4 -2 -3 -11 6 9 -12 7 and 10. So I didn't show all the work here in computing the inverse, take up a little bit too much space, but that's basically how you would do it. You can verify the computations. Now let's look at T inverse. So that would be given by x1, x2, x3. I take T inverse, apply it to that, and I get A inverse times x1, x2, and x3, which is the same thing as 4 -2 -3 -11 6 9 -12 7 10 times x1, x2, x3, which is 4x1 minus 2x2 minus 3x3 minus 11x1 plus 6x2 plus 9x3 and minus 12x1 plus 7x2 plus 10x3. So we have found a formula for T inverse of x1, x2, x3, which we can rewrite in the same fashion as they wrote T in, to be 4x1 minus 2x2 minus 3x3 minus 11x1 plus 6x2 plus 9x3 minus 12x1 plus 7x2 plus 10x3. The fact that A inverse even exists is enough to say that T is 1-to-1. We found T inverse, so we're done. If T from V to W is a 1-to-1 linear transformation with range R of T, and if W is any vector in RT, then the fact that T is 1-to-1 means that there is exactly one vector V in V for which T of V is W. This fact allows us to define a new function called the inverse of T, denoted by T inverse, that is defined on the range of T and that maps W back into V. As we just saw in the previous example, we can find these inverses in any case where we have a 1-to-1 and onto transformation. So let's find the inverse of the linear function T from Pn to Pn plus 1, given by T of P of x is x times P of x. So let's look at what happens to T of some polynomial, let's say C0 plus C1x, and so on through Cn xn. Well, that just takes each term multiplies by x, so C0x plus C1x squared, and so on through Cn xn plus 1. So to get backwards, let's take T inverse of C0x plus c1 x squared, and so on through cn xn plus 1, and we will just drop the x and get c0 plus c1x, and so on through cn xn plus 1. Remember that this inverse operation, this inverse transformation, is only defined on the range of the original transformation. So we can only insert vectors over here that we could possibly have gotten out of the original transformation. So we wouldn't be able to put this vector back into the inverse. As an example of what this does, look at t inverse of, let's say, 2x minus x squared plus 5x cubed plus 3x to the fourth. So then you drop the x and you just get 2 minus x plus 5x squared plus 3x cubed. Everything just goes down by 1 power. If t1 from u to v and t2 from v to w are linear transformations, then the composition of t2 with t1, denoted by t2 circle t1, is the function defined by the formula t2 of t1 of u, where u is a vector in u. If t1 from u to v and t2 from v to w are linear transformations, then t2 circle t1 from u to w is also a linear transformation. So if we have two linear transformations and we compose them, then the composition is linear still. Let's prove this. If u and v are vectors in u, and c is a scalar, then it follows from the linearity of t1 and t2 that we can take t2 composed of t1 of u plus v, rewrite it as t2 of t1 of u plus v, but t1 is linear, so t1 inside of t2 splits up as t1 of u plus t1 of v, and then t2 can split because t2 is also linear, so that splits as t2 of t1 of u and t2 of t1 of v, which is the same thing as t2 circle t1 of u and t2 circle t1 of v. So addition splits. Let's look at scalar multiplication. Well, t2 applied to t1 of c times u, the c can come out of t1 because t1 is linear, but then t2 is also linear, so the c can come out of t2, which is c times t2 circle t1. So both linearity properties are satisfied. Let's let t1 from p1 to p2 and t2 from p2 to p2 be linear transformations given by these formulas, where t1 is this xp of x we've seen, and t2 is the polynomial evaluated at 2x plus 4. How about we find the composition t2 circle t1 if p of x is equal to c0 plus c1x. So let's write out t2 circle t1 p of x is equal to t2 of t1 of p of x, which is t2, well, t1 just takes p of x and makes into xp of x, but then t2 just takes whatever's inside and plugs in 2x plus 4. So x gets replaced with 2x plus 4, and p of x gets replaced with p of 2x plus 4. But then we have that p of x is equal to c0 plus c1x, right? That's what they told us. So that means that we have t2 circle t1 of p of x equal to t2 circle t1 of c0 plus c1 of x by plugging in. And we'll just plug it in right over here. So that's 2x plus 4 times c0 plus c1 times 2x plus 4. We already found that the transformation had to be 2x plus 4 times p of 2x plus 4 to begin with, so we leave the 2x plus 4, and then p of 2x plus 4 is this thing with 2x plus 4 plugged in for x. So that's what we did. So we can rewrite that as c0 times 2x plus 4 plus c1 times 2x plus 4 squared by distributing. If t from v to v is any linear operator, and if I from v to v is the identity operator, let's show that for all vectors v and v, that t circle I and I circle t are the same as t. Well, let's look at t circle I first. Apply that to some arbitrary vector v. Well, that would be t of I of v. And I of v is just v, so this is just t of v. Well, how about if we go the other way? Let's do I circle t of v. Well, then that would be I of t of v. But I of anything is itself, so that's just t of v. So that means that t circle I is equal to t, and I circle t is equal to t. Compositions can be defined for more than 2 linear transformations, right? There's nothing really stopping us here. We can go from u to v, then from v to w, and then from w to y. So we can compose 3 transformations. We would get t3 circle t2 circle ti. We just keep plugging one into the next one. If t1 from u to v and t2 v to w are 1-to-1 linear transformations, then t2 circle t1 is also 1-to-1, and t2 circle t1 inverse is t1 inverse circle t2 inverse. So the order changes. So you have to be a little bit careful here. But let's prove it real quick. We want to show that t2 circle t1 maps distinct vectors in u into distinct vectors in w. But if u and v are distinct vectors in u, then t1 of u and t1 of v are distinct vectors in v, since we assumed to begin with that t1 is 1-to-1. Right, that was what we originally stated. So this and the fact that t2 is 1-to-1 imply that t2 of t1 and t2 of t1 of u and t2 of t1 of v are also distinct vectors. But these expressions can be rewritten as t2 circle t1 of u, t2 circle t1 of v. So that means that these guys are distinct. So t2 circle t1 maps u and v into distinct vectors in w. Okay, so that means that t2 circle t1 is 1-to-1. Let's do part b. We want to show that t2 circle t1 inverse is t1 inverse circle t2 inverse for every vector w in the range of t2 circle t1. So how about we let u equal t2 circle t1 inverse. Our goal is to show that u is t1 inverse circle t2 inverse. Okay, so we have that u is equal to t2 circle t1 inverse. So that means that t2 circle t1 of u is what produces w, right? Because if u is the inverse of w being plugged in, then that means applying the original t2 circle t1 to u is what produced the w. Right, you just go backwards. But that's the same thing as saying t2 of t1 of u is w. And now let's just do t2 inverse of both sides. And then we take t1 inverse of both sides. And notice that changes the order. You want to do the t2 inverse first to cancel this t2. And then you want to do t1 inverse to cancel the t1. And that way you can have u equal to t1 inverse t2 inverse of w, which is exactly what we wanted to prove.